Deep learning models are growing rapidly in size, and the data volumes they process are expanding at an even faster rate. To keep up, we are building massive data centers, but traditional silicon processors are hitting tight economic and environmental limits. As you try to model complex systems like molecular interactions or large-scale supply chains, you run into the curse of dimensionality. Adding more classical servers to solve problems that scale exponentially eventually becomes too slow and too expensive to maintain. Some headlines suggest quantum AI will soon make classical deep learning obsolete. That is a false choice. Tech leaders must now pinpoint the specific, high-complexity mathematical subroutines in their existing AI pipelines that require quantum coprocessing today. To understand what to hand off, you have to look at how these systems manage information. A classical computer uses bits. If you have an n-bit register, it can only store and process one n-bit number at any given moment. The system scales linearly. Quantum computing scales exponentially. An n-qubit system represents 2 to the power of n states simultaneously through superposition. A qubit isn't just 0 or 1, it's a complex combination of both, letting a quantum machine explore a massive landscape of possibilities all at once. That exponential capability is suited for mapping high-dimensional relationships. It is, however, unnecessary and highly inefficient for straightforward linear data processing. Long short-term memory networks, or LSTMs, are currently the gold standard architecture in classical AI for analyzing sequential information. Because of their specialized internal memory gates, LSTMs excel at continuous value regression. If you need to predict a specific number, like next quarter's revenue or a precise temperature reading, they produce incredibly low error metrics. But they are also brittle. An LSTM's performance relies heavily on specific ADA characteristics and extensive hyperparameter tuning. When applied to chaotic, noisy datasets with millions of variables, classical models often fail to identify weak predictive signals unless given unlimited optimization time. Classical AI provides robust fidelity for standard data forecasting. It chokes when forced to find non-obvious patterns in chaotic, high-dimensional environments. This diagram shows the variational quantum algorithm framework, the most pragmatic bridge between classical and near-term quantum hardware. Inside this loop, a variational quantum classifier projects classical data into a massive exponential feature space, searching for hidden boundaries that a classical model would miss. We are currently in the noisy intermediate-scale quantum era. Physical qubits are highly sensitive, losing their quantum states quickly, and turning outputs to random noise. This creates a reality gap. While software simulations show high accuracy, on actual physical hardware, gate errors and decoherence heavily degrade the performance. Yet, even with degraded output, these quantum classifiers demonstrate a statistically significant ability to recognize complex patterns that classical models overlook. Their current value lies in that highly specialized exploration. There is a practical hurdle stopping widespread adoption. Before a quantum processor can evaluate classical data, that data must be encoded into a quantum state. This translation process is a severe bottleneck. In many cases, the time required to execute complex feature maps takes longer than the computation itself, neutralizing the speed advantage the quantum processor provided. You also run into barren plateaus. If you try to capture more complexity by adding depth to your quantum circuit, the training landscape goes flat. The classical optimizer receives zero mathematical signal, and training fails. Researchers are actively testing workarounds, like quantum oracle sketching, which processes classical data as a continuous stream on the fly to bypass memory limits. Until data loading and barren plateaus are solved across the board, pure quantum AI cannot ingest raw, unstructured big data at an enterprise scale. If allocating resources today, tie your decision framework directly to your bottleneck's mathematical structure. For high-fidelity, continuous value forecasting with well-structured data, route capital to scale up classical deep learning. For intractable, high-dimensional classification problems or massive optimization constraints, route engineering to a hybrid quantum framework. The trade-off for enterprise leaders is capital allocation. Investing in cloud-based hybrid infrastructure today means hiring specialized quantum talent for a return on investment that is realistically years away. For data scientists, the trade-off is time. Shifting focus to learn quantum algorithms means you will spend your days fighting hardware noise and gate errors rather than shipping immediately deployable consumer applications. Smart resource allocation means matching the architecture to the data. Use classical models to achieve fidelity, and deploy hybrid quantum models when you need exponential expressivity. Ultimately, these two paradigms exist in a codependent symbiosis. They aren't competing for the same tasks. AI for quantum is already happening. Engineers are training classical neural networks to monitor qubits and apply real-time error corrections to stabilize the hardware. Quantum for AI will follow. Quantum processing units will eventually act as specialized accelerators, handling only the most mathematically intense subroutines of massive AI pipelines. The competitive advantage in 2026 belongs to the organizations that master seamless hybrid integration. Scaling raw qubit counts is secondary to building the systems that allow these architectures to work in tandem.